Self-cooling is a relatively new concept applicable to termite mounds, but for the first time will become applicable to human habitat because the secret of the shy creatures has become uncovered and can be adapted to suit our own needs. Sustainability and affordability occupy the two extreme ends of the cost spectrum. However, this project will attempt to bridge the gap. There is no single magic bullet to solve sustainability. It's a multi-pronged approach requiring every stone to be turned and backed up by scientific research. Affordability is considered over the entire lifespan of the project and not just the initial outlay of the project. Let's get started with thermal insulation. The diagram shows the relative thickness of different building materials needed to give the same insulation value. For example, brickwork provides some thermal insulation, but the thickness will need to be about 20 times that of modern insulation board of expanded plastic to give the same insulation effect. Similarly, concrete has some insulation but will need 48 times the thickness of EPS to achieve the same U value. This suggests that concrete is the worst possible material to use when it comes to thermal insulation. Secondly, let's look at thermal response between heavyweight construction and lightweight construction. The diagram suggests how it is possible for two types of wall to have the same thermal insulation as measured by U values, but to absorb or dissipate heat at different rates. As a result, room inside such walls will take different time to warm or to cool. In general, lightweight structures respond more quickly to surrounding temperature changes than do heavyweight ones. This is because heavyweight materials have higher thermal capacity and require more heat energy to produce changes in temperature. These effects are shown further in the next slide. Thermal response with time. The graph shows that lightweight structures have short lag time. What it means is that it takes a short time for heat to travel from the outside surface to the inside surface, whereas heavyweight structures have long lag time, and that means it takes longer for heat to travel from the outside surface to the inside surface. This is a particular quality that we'll be looking for in our quest for self-cooling homes. Temperature gradient through a wall. A structure made up of different materials will have varying temperature gradient between the inside and outside. The layers with the highest thermal resistance will have the steepest gradients. This is because the best insulators must have the greatest temperature differences between their surfaces. It's also useful to point out that 1. Steeper graph gradients link to higher condensation risks. And second, the ratio of the temperature changes inside the structure is proportional to the ratio of thermal resistances. So although it may seem attractive to just simply attach insulation to the back of a blockwork to increase its U value, the risk here is that you end up with condensation, which in time will cause the insulation to rot. Solar intensities forces us to consider the shape of our buildings. And in the tropics, it is unwise to use horizontal surfaces or flat roofs, as the graph suggests, peak solar intensities. What it simply means is that because the sun moved directly overhead, it is simply not clever to use flat roofs in tropical regions. Temperate zones, on the other hand, is useful to point out. For vertical surfaces, the peak solar intensity occurs in spring and autumn, around the time of the solstice. Most solar heat gain to buildings is by direct radiation through vertical windows. This heat gain via windows can, if used correctly, be useful for winter heating in temperate zones. What it simply means is this: a tall glass building in Europe is suitable for that environment, but totally inappropriate for tropical zones. And that if you try and do the same in Africa, you end up with more than what you bargained for. In the scientific studies that preceded this, we found that for every stone that was turned, the termites got there before us. Termites built gigantic mounds inside of which they farm a fungus that is their primary food source. The fungus must be kept at exactly 30 degrees centigrade, while the temperatures outside ranges from 22 degrees at night to 37 degrees during the daytime. The termites achieve this remarkable feat by constantly opening and closing a series of heating and cooling vents throughout the mound over the course of the day. With a series of carefully adjusted convection currents, air is sucked in at the lower part of the mound, down into enclosures with muddy walls, and up through a channel to the peak of the termite mound. The industrial termites constantly dig new vents and plug up old ones in order to regulate temperature. This is an English barn. The question is this type of building appropriate for tropical regions? The answer is yes, for a different reason. The high-pitched roofs are designed for temperate regions to avoid snow loading, but the same can be used in tropical regions to combat solar heat gain, as only half the roof receives direct sunlight while the other half remains in shade throughout the day. This is the Ramsey Training Center at TBTV. I went in there. It was baking hot outside, but the inside remained cold. This type of building is appropriate for the tropical environment, even though it's based on the English barn. This is a typical example of missionary buildings during the colonial days. Note how the walls are shaded from sunlight by surrounding veranda. The open eaves and thick walls keep the inside cool. Another example to look at is the Eastgate Center in Zimbabwe. The Eastgate Center in Harare, Zimbabwe typifies the best of green architecture and ecologically sensitive adaptation. The country's largest office and shopping complex is an architectural marvel in its use of biomimicry principles. The mid-rise building, designed by architect Mick Pierce in collaboration with Arab engineers, has no conventional air conditioning or heating, yet stays regulated year-round with dramatically less energy consumption using design methods inspired by indigenous Zimbabwean masonry and the self-cooling mounds of African termites. The Eastgate Center uses mechanical ventilation to draw in cool night air to cool the building. The center uses less than 10% of the energy of a conventional building of its size. These efficiencies translate directly to the bottom line. Eastgate's owners have saved $3.5 million alone because of an air-conditioned system that they did not have to implement. Outside of being eco-efficient and better for the environment, these savings also trickle down to the tenants whose rents are 20% lower than those of occupants in the surrounding buildings. Who would have guessed that the replication of designs created by termites would not only provide for sound climate control solutions, but also be the most cost-effective way for humans to function in an otherwise challenging context. Unlike the Eastgate Center, this is the first attempt to use natural ventilation in a true sense of the termite tradition to cool the house. That is relying on natural ventilation and the buoyancy of hot air to rise and escape to be replaced by cool air below, as well as harnessing the drop in temperature during the night. This can be achieved through careful design and placement of vents at the upper aspects, as well as implementation of simple measures such as opening windows and vents during the night to flush the house with cool night air while limiting air intake during the daytime. Also using materials of high thermal resistance to keep the cool air for as long as possible until the next cycle of cool air at night. In addition, the footprint of the house is reduced considerably by placing the rooms in the loft-over living spaces on the ground floor, thus freeing up the site for landscape to bring nature into the habitat. It also helps with sustainable urban drainage system by allowing rainfall to penetrate into the ground and avoiding runoff turning into floods. Natural ventilation is achieved through a series of interconnecting ductwork. For instance, the ground floor living spaces are exposed to the loft via strategically cut out ductwork in the floor slab above to one side, indicated by the white shaded areas on the plan. This relies on the buoyancy of hot air to rise into the loft space and be replaced by cooler air from below. The bedroom in the first floor are all exposed to the loft above and have no ceiling. The master bedroom below the studio in the second floor attic is extended beyond the attic wall to give exposure to the roof, indicated by a white shaded area at the front of the building. The ventilation duct cutouts in the first floor are connected to adjustable louvers adjacent to the balcony walls. This ensures that the rising hot air from the living areas can escape above through the side walls of the balconies. The ventilation ducts in the first floor cutout are connected to adjustable louvers adjacent to the balcony walls. This ensures that the rising hot air from the kitchen and dining areas can escape above through the side walls of the balconies. The ventilation through the stairwell is connected to adjustable louvers adjacent to the studio balcony walls. This ensures that the rising hot air from the staircase below can escape above. Likewise, the master bedroom ceiling vents are connected to the right-hand side adjustable louvers. The best stage to incorporate the termite concept is at the design stage, where careful planning at the beginning is crucial in terms of materials used and strategic placement of vents in the structure as well as the roof of the building. Failing that, you can always do a retrofit, but that might require some painful adjustment and expensive reworking of the original design. The design of the plumbing system is very compact to ensure minimum pipe work and no redundancies. A single soil and vent pipe (SVP) connects to all the sanitary units and is ventilated at the top above the roof. To illustrate the principle, you can lift a column of liquid using a straw from a bottle of Coke. If the top end is sealed with your thumb. However, if you let go your thumb, the liquid will drop under gravity. Opening the top of the SVP and connecting to all the sanitary wire uses the same principle to ensure that water discharges downwards with ease into septic tank without blockage in any part of the pipework. Keeping the cool inside the building during the daytime requires correct use of materials with better thermal resistance such as bricks, hydrofoam blocks, timber decking and clay roofing tiles, as well as ensuring minimum solar gain by use of canopies and roof overhangs. Bedroom walls are concealed in the loft spaces. That means walls are not exposed to sunlight, with the added bonus of only one side plastered and painted, saving up on construction costs and making it more affordable. Trees can be strategically positioned to cast shadows on walls that are exposed to horizontal rays during sunrise and sunset, that is, if east-west orientation is unavoidable. The steep angle pitch roof ensures that only part of it is subjected to direct sunlight while the other parts remain under shade most part of the day to minimize solar gain compared to flat roof which overheats all day. The vents positioned at the apex of the roof ensure stack effect and air movement throughout the building as hot air rises to escape at the highest point. Openings in opposite walls ensure maximum cross ventilation. Integrating a summer hat into the design extend the living area into the natural environment, which improve comfort levels and well-being. Appropriate detailing and use of cavity walls as well as window and door sills in the context of tropical environment can improve thermal qualities of the building to keep the cool in and reduce maintenance costs. In particular, the thicknesses of cavity walls and materials used can improve the lag time for heat transfer between the outside and inside wall surfaces. A lag time of 8 to 10 hours is sufficient delay to enter the next cycle of cool night air in order to induce perpetual cooling effect. It is anticipated that inside temperatures would range from 5 degrees centigrade to 10 degrees centigrade below normal outside temperatures depending on geographical location. For example, in Abitifi, where average night temperatures are around 22 degrees centigrade and nighttime temperatures 32 degrees centigrade, 10 degrees centigrade cooler inside is possible. In Accra, where night temperatures average is around 26 degrees centigrade, while daytime around 32 degrees centigrade, it will be possible to achieve 6 degrees centigrade below normal average temperatures. Thank you for listening.